Section 5.3, Equations of Equilibrium. So previously we stated that the necessary and sufficient conditions, for equilibrium requires that the sum of the forces that's subjected to that free body diagram would result in a force that has a component of 0I plus 0J plus 0K. In other words, we'll have the sum of the forces in the X, and that'll equal to 0. Sum of the forces in the Y, and that'll equal to 0. And if we're in a three-dimensional system, the force in the Z, the sum of the force in the Z should also equal to 0. And when we're doing this type of problem, you have to make sure that you're defining your X, Y, and Z coordinate system. The other requirement was that the moment, or the sum of all the moments that is being subjected to that body, whether it's applied moments or moments due to forces, it should add up such that you get 0I plus 0J plus 0K. So in other words, you're going to be taking the sum of all the moments and it should go to 0. And what you're going to do is take it about a point. And you can choose that point to be any point. Let's look at a problem to illustrate how we can apply these equations of equilibrium to a rigid body. This is problem number 510 out of Hibbler's 14th edition. So here we have a beam subjected to a 6 kilonewton point load, and we have this cable that's attached here, and a force of 4 kilonewton is applied, and they give us some dimensions, and we should note that it's supported in this wall. So this is our given. Our required is, so they want to know reactions at fixed end A. So here's our solution. We have to draw the free body diagram. So I'm going to idealize that beam like this. And I'm going to draw the 6 kilonewton force. And I'm going to draw that 4 kilonewton, and it pulls in that direction. So I've freed this beam from its support, and I know that the wall prevents this beam from translating in the X direction. If I define my coordinate system like this, X, Y, since it prevents it from translating in the X direction, I would have a reaction force in the X. So I choose it to go in the left or the negative X direction. The wall also prevents the beam from translating in the Y direction. Therefore, I will have a reaction force in the Y. So I'll do that. This is my AY. And the wall also prevents this beam from rotating. So it'll have this reaction moment, and I'll call this M at A. So those are all my reaction forces. This is my complete free body diagram. It has a coordinate system. It has all my reaction forces and moments at the support. And I also have the externally applied forces of 6 kilonewton and 4 kilonewton here. The equations of equilibrium now can be applied. Equations of equilibrium. And that means I have to take the sum of all the forces in the x direction, and I have to set it equal to 0. So that would mean that I would have my y component here, which would be 4, let's see here, this is 60 degrees, so that would be 4 kilonewton cos 60, and my x component of that would be 4 cos 30. So I would have a negative ax plus a 4 cos 30 equal to 0. I can solve for ax, and ax should be 3.46 kilonewton, and I get a positive. And what this positive means is that I guessed correctly in terms of the direction on my free body diagram. So next, some of the forces in the y. I'll have my positive ay minus my 6 kilonewton force minus my 4 cos of 60, and that'll equal to 0, and I should get ay is equal to 8 kilonewton. Now, it being positive, what that means is I guessed correctly. That means the direction of my ay force should be going up. Next, I have to ensure that the moment about any point must equal to 0. And I think what I'm going to do is choose it to be at A, because if I choose it at A, then I don't have to consider the moment of AX and AY, because they won't cause any moment about A. But you can choose it anywhere you want. Like, for example, you can choose it here, let's say, at B, and calculate the sum of the moments about point B. So sum of the moment about point A is going to equal to 0. So that'll be 1.5 times 6. 1.5 times 6, and that'll be a negative. So this distance right here, since we know that it's 30 degrees because it's given in the problem statement, that would mean this distance would be 1.5 times the cos of 30. So going back to this, that would be, the moment arm would be 3 plus 1.5 cosine 30. 3 plus 1.5 cos 30 times this force, 4 cos of 60, and it would be a negative. We need to take into consideration that force, so that would be a negative times a moment arm of right there, which that would be 1.5 times sine of 30 degrees. So that would be 1.5 times sine of 30 degrees times 4 cos of 30. And what we have to do is add this reaction moment MA. So that would be MA, and that all should equal to 0. We have one unknown. We solve for that, and the moment about point A would have a value of 20.2 kilonewton meter. So the reactions at A are at this moment, this y component, and this x component. Let's do another problem. What we have is a beam, and it's supported by a pin here. and we'll call that point B. It's also supported by a rocker right there. And there's a distributed load that looks something like this. And the forces go in this direction. And they tell us that this is 800 Newton per meter. And what's required is for you to find the reactions at the support. Reactions at the supports. So here's the solution. And I won't solve it for you all the way, but what I will do is draw the free body diagram for that structure for you. So I draw the structure, and here's my point A. That's my point A. My point B is right there. So at the support, the rocker assembly prevents this beam from translating in the vertical direction, because the rocker is sitting on this horizontal ground. So my reaction would be going upward. So that would be normal at A. At point B, this pin assembly prevents this structure from translating in the X with a coordinate system as shown. Therefore, since it prevents translation in the X direction, it would have a reaction force in the X direction. This also prevents the beam from translating in the Y. Therefore, I would have a reaction force in the Y direction. This would be BY. The pin support doesn't provide any resistance for this beam in terms of rotation. Therefore, there will be no moment reaction at B. Same thing for the rocker assembly at A. This rocker assembly doesn't resist any rotation. Therefore, there will be no moment reaction at A. So this is your free body diagram. What we also have to do now is take into account the distributed loading. So the distributed loading was rectangular. So the equivalent would be the area of this rectangle, and it would act at the centroid of the rectangle. Therefore, it would be in the middle. So make sure you calculate this entire distance and then apply your resultant force right there. So NA should come out to be 3.33 kilonewtons. BX will come out to 2.40 kilonewtons, and BY will be 133 newtons.